Good morning. Today in this video lecture, I'll explain the bioeconomic model of fishery resources. So, of a particular fisheries, we have the data of catch and effort, and we have also collected the cost and price data. And then, how do we model the fisheries in terms of economy? So, bioeconomic model of a particular fisheries. So let's see that we have a year-wise catch data and effort data. Then we calculate the CPV, catch per unit effort, so catch by effort. Then we have collected the cost and price data, so cost per boat, so that cost is associated for the fishing. So one boat is going for fishing, so how much cost is giving, means the cost of fuel cost, the maintenance cost, the labor cost, then the repairing cost, then the different ice cost, then the food, beverage, and the other miscellaneous cost that is associated of the fishing. So that cost data year wise, and the total cost means what is the per boat wise, and then the total number of boats into the total cost and the price, how much price of the fish. So particular fish is per kilogram, this is the price, market price. So then to convert it into the metric ton. Okay, so this is the basically input data, and then we have calculated the biological references data, that is the carrying capacity, catchability coefficient Q, then R biological growth rate, then maximum sustainable yield. So these are the data we have calculated from the log normal separate model using the CET software. So this is done. Then next you can calculate this is the thing that PMSY and FMSY, but it is not required for this bioeconomic model. So it's basically used for the stock prediction. This is the thing, but for now it's basically for bioeconomic model, it's not required. So this is our input data, and we have calculated the biological reference point from CET software. It's done. Next you can do some basic statistical analysis of your data set. You can estimate the descriptive statistics, mean, median, mode, then the standard deviation, standard error. So this is the basic statistical analysis, and you can also do a regression analysis of the catch and effort. So you just do the catch and effort. So you go to your data and data analysis, then the regression, and you plot your y-axis, that is the prediction. Y means y-axis, that is the prediction. So we want to predict the catch if we know the effort. Okay, so this much of number of boats is operating in the whole of one course. Then what will be the cost, what will be the catch of this particular fishery next year? We can predict it. So that is the regression model. So you put y-axis the catch and x-axis is the effort, then put in the level and the confidence level 95%, then output range where you want to see your output. So this is the output range, and then just click OK. You will get your regression model, and this regression analysis is highly significant as p-values is less than 0.01. And so this is the basic descriptive statistics, and then price and cost data. So year wise we have the catch, effort, cost, and the price. Okay, so you plot harvest means that is the catch by price. So here's a catch and the price. Okay, so you plot it, then you will get, you just plot a simple regression line, and from the simple regression line you can get the slope and intercept value. So if you want to check it, just go and insert and just plot it. Okay, so then you just add a regression line, and you can get the A and B value, intercept and slope. So A value 4.2929, and B, that's the intercept and slope, that is 5 minus 5 to 8960 minus 5 to 59 or 60, that is the in same. So that is the cost means price over the fish price. Okay, now cost that is associated with your effort. next is the total effort with the total sorry, not total cost, so total effort by your cost. Okay, so this is you plot in a file and then put your regression line, and you can get the slope and intercept value, and this slope and intercept value is used to calculate the total price and total cost. Okay, so price and cost it can be calculated. So price is equal to your means a value, that is the your basically the intercept value into last catch. So into your B17 means your last catch. Okay, so that is the last catch into B17 plus your slope. Okay, intercept into your last catch into slope, so that you will get your price, and your cost, you will unit cost you will get that the same equation, that your intercept into your effort, last effort plus your slope. Okay, so then you will get your price and cost. This price and cost will be used for the analysis. So go to the optimal. So here in optimally we estimate the optimal effort, optimal harvest, optimal effort E star, optimal harvest that is H star, and optimal biomass, that is the X star. So we have calculated this KQR earlier, so this KQR is always required. So KQR you have calculated the C and P just now, because price and cost data. So C and P we are taking from here, and a delta is the discount rate. It is important now. Okay, so delta is the discount rate. That discount rate means 0 to 1 varies. So 0 to 1, that is the percentage, because basically 1 means 100%, 0 means 0%. Okay, so that discount rate means that how much we are allowing the fisheries to the in terms of effort, in terms of area, in terms of number of days of fishing. So every time, so this is the one means delta is 1 means 100%, means it is a totally open access fishery, so there is no restriction. So 100% is open. Anyone have the boat, anyone have the net, it can see, he or she can go and do the fishing. Okay, and 0% means this is totally ban, no one go for the fishing, so 0. And so what will be the optimal discount rate to get the sustainable harvest effort and biomass, so that is the stock. So we how we'll calculate this one. So just you plot your KQR and cost and price, and the delta that is the 0 to 1, that is the 0% means totally restricted fish, no one can go, the fishing is not allowed. 1 means 100% fishing is allowed, it is totally basically open access fisheries. And then the 1%, 5% allowing 5% area, then the 10%, 20%, 30%, 40%. So what will be the optimal? So 20%, 10%, 30% means I am allowing 30% of the total effort back can be go for the that particular fishery for fishing, and 30% of the total area it's allowed for the fishing, or 30% of the total days, number of days means in a year 30% of 365 days I am allowing to go for fishing. So that is called a discount rate, that is the restriction. And but in our fisheries is open access, so it's 100% allowed. So but not 100% allowed, but few restriction is there, few ban period, few zone restriction is there, so it is not totally 100%. But restricted fisheries is much more important to make it sustainable. So then delta, then how your X will be calculated. X equation, I'll give the equations of how to calculate X star, H star and E star in a separate sheet. So this is the big equations of X star. Calculate how to calculate the X star. It's a very big equation. You can see this is the equation. Okay, but this equation is related to your biological required your biological data. So K, Q, R, cost, price, and delta. Okay, so then you go. Then you X star you have calculated. Then go to calculate the H star. H star is also the equations is required your R, then you required your X star, then you have to required your K, means the carrying capacity also. Okay, then E star you can calculate it R means is your H star is required to calculate the H star, and then L and QL means your catchability coefficient, and Q means your biomass, optimal biomass. Okay, so then from this equation, you can also calculate it H star, and the pi values, and PV means PV, that is also required to estimate the profit. Okay, so that is the profit. Okay, so PV is the profit, so we'll see the profit 0 to highest profit. Okay, so this you can calculate it from those equations. So I'll keep a separate sheet for the equations, for the methodology of this analysis. And after making these tables or making this calculation, you can plot here your optimal biomass, optimal harvest, and optimal effort at different discount rate. So if you have the different discount rate, this is one means 100% discount rate, means totally open fisheries, and 0 means fishing is totally restricted. Okay, so how the biomass, optimal biomass, and harvest and effort will varies in different discount rate. So you see that biomass and your harvest is almost very high in if there is no fisheries. Okay, so no fishing is allowed, so means biomass is very high. But if you increase your discount rate, your biomass is going to decline. Okay, so what will be the optimal biomass? Means it is not that we are not allowing the fishing. We have to allow the fishing. So almost 20 to 30% is almost a optimal. So you can see that optimal harvest, optimal effort, and optimal biomass is also, so 20 to 30% for this particular fisheries is the optimal. Okay, and if you increase your opennesses, means 100% open, so there is the biomass is the, how much is the low, you can check your biomass is totally low at that level. Your harvest is also low, but effort is increasing, your effort mean number of boat is increasing day by day. That is the things. And if you check your optimal profit in different discount rates, so different discount rate, you can check your profit. That profit is also, if you increase the high discount rate, means if you allow the whole fisheries for fishing, then you can check that your profit is almost going to be very low. And so optimal profit will be also 20 to 30% if you, that will be very good. Now comes to the how to calculate the effort MSY, harvest MSY, and biomass of MSY, and the TR, total revenue, TC, total cost, and the TR minus TC means the profit. Okay, then how to calculate the tax, that is also important. So tax, landing tax, and effort tax. So the landing tax and effort tax of MSY, MEY, and OSY. So effort MSY is very easy. Effort MSY is equal to basically the equation, all the equation I will send to you, no problem issues. Okay, so effort MSY is basically is coming from this biological parameter. B5 means B5 means the R by 2 into B4 means that's the Q, R by 2 into Q. Okay, so that is the effort MSY. Effort then harvest MSY is equal to this equation. Then the biomass X MSY means biomass of MSY is equal to K by 2, means K by 2 means carrying capacity by 2. So this is the equation you can estimate the MEY of this equation. Harvest of MEY is, you have to calculate from this equation, and biomass of MEY this equation. Then optimal open access equilibrium, harvest, effort, and biomass. Then your total revenue, is coming from the cost into the cost, means total revenue is basically come from the price, and E3 is the your harvest, price into harvest. Total cost is equal to your cost into your biomass, cost into your effort. Okay, cost into effort. So TRTC, and profit mean TR minus TC, that is total revenue minus cost is the profit. Very simple equation we know. So in different levels, so MSY, MEY of all those things, and open access equilibrium of all those three we are calculating. So that is very good. Means if you check this thing. So check the effort. Okay, effort. So EMSY, check the EMSY. Now how many number of boats is operating in this zone? So now the boat is operating 34,543 boat is operating, number of boats is operating in that region. But what will be the optimal, or the MSY effort will be 31,000. So there is almost 4,000 boats is more than the sustainable limit. So you have to reduce this, and if you check the MEY, almost 30,000 boat is the very good, they will make the maximum profit. But now the boat number of boat is almost 34,000. And open access, if you make it open access, give the 100%, then the 61,000 boats you can operate it. But in most important things, if you go to my bioeconomic lectures, and then you can go that open access equilibrium, your total cost, minus total revenue minus the profit is zero. Okay, you see the graph, total cost, total revenue, so the profit is zero. So that is called the tragedy of the common, that point. Okay, so when the paper goes to your profit is zero, means whatever your total cost is equal to your total price. Okay, total revenue. Okay, so that is, and you have to calculate the landing tax. That is the simple equations of these equations. I'll give the equations: landing tax of MSY, effort tax of MSY, landing tax of MEY, effort tax of MEY, and open access what will be the tax. That tax is also incorporated in the next cost sheet. That is, we have already discussed these things, how to collect the cost sheet. So diesel or the fuel cost, ice cost, groceries cost, transport cost, boat cost, per trip, and the total how many trip and crew members. So everything you will calculate the cost per year. Okay, now comes to the effort, MEY, MSY, and OSY, optimal sustainable yield. How to calculate the optimal effort of MEY, optimal effort of MSY, and optimal effort of open access equilibrium. Okay, so that values, these are the values we have already seen in the previous table, but how to get these graphs? Okay, so for this we require the KQR value, that already calculated. We require the C and P value, and the delta is 0.01. And you check effort, you just make a simple scale up to your optimal, maximum optimal, or whatever you can make the graph comfortable to or maximum optimal. You make the effort. So effort 0, make a simple scale 0. I have to reach this one. Okay, so I have to give 0, 5,000, maybe 10,000, 15,000, 20,000, this much, or scale, or I just make it here 0, 3,500, then the double 7,000, then plus 3,500. So that is a simple scale. Okay, so to make a optimal limit, or just to make the graph. Okay, so and then K value, carrying capacity values, fixed Q, fixed R, fixed cost, price, and T1, that is the tax. Okay, so T1, that is the tax. So this is the effort MEY tax. Effort MEY tax we have already calculated. Effort in MSY this one, MEY this one. Okay, so effort MEY, so effort MEY I have calculated effort MEY tax. Okay, so that is also required here. Okay, now to calculate TR, TC, and TC of MEY. TC of MEY basically total cost. This is total cost after the tax. Okay, so because the fisheries is a non-taxable, so if you have boat, if you have natural resource, must have a tax. Okay, so because natural resource is there, if you have boat, if you have the net, you go on fishing, but you are not giving any tax to the government, so that is not so. In tax incorporation, to incorporate tax, that is also one of the good management practice. Okay, so how to calculate the tax? So this is TC1 of MEY, that is the tax, total cost after the tax, and the pi is the total profit. Okay, so we have to calculate TR, TC, TC1 of MEY, and the pi. Okay, So this is the equations are there. So TR, how to calculate the TR, how to calculate the TC, and how to calculate the TC of MEY, and how to calculate the pi. Okay, so this is the pi means the profit, that is the profit. Okay, TR minus TC. Okay, normal profit. So this calculate you have to done, just put the calculation and just scroll down, it's automatically you just get. Give the calculation, your calculation on the equation, and just scroll down, you will get your result, and then plot these things. Okay, so this is plot, this plot is of, this is the plot. Okay, so TR, TC, TC1 of MEY, and pi. Okay, so in terms of effort, so this is the effort, x-axis is your effort, and y-axis is your TRTC, means that is the cost, that is the amount or money, that is the money, money, real or dollar or whatever it is. So the cost, total cost, this is the total cost line. So we know that if import is increasing, the cost is also increasing. Number of boats you are increasing, the cost is also increasing. And this is the revenue line, TR revenue line, and then the TC of MEY, total cost after the taxation, this is, and the profit, the profit line. Okay, so so this is the total cost line, and TC of ME after tax, this is the cost. Okay, TC1 FM. So this is the total cost line, and TC1 of MEY, this is the line. And so what will be the middle term? So this is the effort MEY. So almost 31,000 something, or 30,000 something boat, 30,000 something boat is good for sustainable economically. Okay, accordingly you have to calculate the effort MSY. So this is the MSY, this is the MSY. Okay, now comes to the MSY, the same equation thing, same equations could be different. TR, TC, TC of 1, and the PR means the bio, this is the profit. Okay, and you are taking the T, that the tax of MSY effort. Okay, so we are calculating effort tax now. So then you just prepare this graph. Okay, and then the open access equilibrium or optimal sustainable yield. Okay, this is the optimal sustainable yield graph. So these three for the effort. Then same thing, you have to prepare the landing tax. Okay, so effort K, Q, R, C, P, and tax of landing tax. If you go to this here, the landing tax. Okay, so take this landing tax of MSY, maximum sustainable yield, maximum economic yield, and open access equilibrium yield, or the optimal sustainable yield. Okay, so landing tax, and you incorporate, and then you calculate a TR, TC, TC1, and pi. Okay, so and then you have to calculate, you have to get this graph. Okay, effort MEY for the landing tax, that will be almost 30 yes, 30,000 around for the MEY. For MSY is almost 31,500 something, and for open access equilibrium optimal sustainability almost 42,000. Okay, so this is the way how do you calculate your effort MSY, effort MEY, your different discount rate, what will be the optimal stock, biomass, and effort. So this is the bioeconomic model of a particular fisheries. Okay, thank you. So if you have any queries, just mail me. Okay, bye.